Hello, physics family. We are going to be talking about projectiles again today, but unlike the previous projectiles where they just had a horizontal motion, which then made them fall, these projectiles are going to be launched at an angle. So something like a baseball player hits the ball on an angle, we know we're going to be able to break those into the X and Y component, but that angle is going to play an important role. So that's what we're going to get into. You'll find that we're actually going to use all of the strategies and math that we've used before, Fab 5, velocity, things like that, but we're going to put it all together to solve some problems. So let's get into it, define, and understand. Okay, so the first thing we have to do is lay some ground rules. When you launch something on an angle, good news, the horizontal velocity is going to stay constant throughout. We're going to assume that there is no, and I mean no, air resistance, okay? So if you take a look at this picture down below, this boy throws something, or this kid throws something at an angle. Notice that the velocity in the X direction, right, stays constant throughout at 12 meters per second forward. That's what I'm saying by the horizontal velocity stays constant. Now the vertical components in the Y direction, remember vertical, anything with Y means up and down. Well, remember X is always the horizontal. That's just going to stay constant velocity. But the Y's, we're going to have to use our Fab 5s occasionally to figure things out. Because why? Because you have uniform acceleration. Remember gravity is always going to be negative 9.8 meters per second squared. And when we have uniform acceleration, we use our Fab 5 equations to figure things out like initial velocity, final velocity, our displacement, which remember our displacement used to be delta x. For this, since we're going in the Y direction, we've been calling that dy. Our time, and then, of course, our acceleration, which really is just our g, our gravity. So we're going to get into that and learn how to solve those problems. But let's look at our projectiles launched at an angle and break that down even more. When we launch something on an angle, really what that is a resultant velocity. So if you're launching something at 20 meters per second on an angle, really that angle and that arrow or vector is the resultant. Remember then, if you have the resultant, you can really break this angled arrow into two components. You have your X component, so this would be the velocity in the X direction, and this would be the velocity in the Y direction. So with that being said, we know our horizontal velocity, right, will stay constant throughout. So that X component, that'll be constant. But our vertical velocity, with every second, it will change. Why? Because an object going up is experiencing gravity, or negative 9.8 meters per second squared acceleration. So remember in the beginning, when we have a projectile, we're going to have a positive velocity because it's going to be going up. When we're at the actual top or highest point of the projectile, remember that that velocity in the Y direction is going to equal 0. Because remember, up and down, we know that the velocity at its highest point is 0 before it starts coming back down. So that is an assumption we can make occasionally. At the top is 0 meters per second. And then remember, at the end, as that object starts falling downwards again, right here, that velocity in the Y direction is going to be negative. So again, kind of a review, common sense, right? But it's good to point these things out because understanding all of this is going to allow us to better understand a problem and then better apply it to figure out, hey, what numbers do I use? What equation do I use? So this was a good review. All right, so say we have our resultant velocity. In this case, we've got our resultant right here, okay? We know that something's being fired on an angle, but what if we want to know the Vx component, so our horizontal velocity, or the Vy? Well, that's when we can do a couple things. We can use the Pythagorean theorem, or we can also use trig. So say I only wanted to find Vy, and yet I knew what my resultant was here. So let's just say, for the sake, I know there's some numbers here, but let's just say this was 100 right here. Could I figure out my Vy quickly? Absolutely. If this is the angle, Vy is my opposite, and 100 would be my hypotenuse. So I could actually just do the sine of 53 is equal to, sine is opposite over hypotenuse, so sine would be Vy, and my hypotenuse would be 100. So by knowing my SOHCAHTOA and knowing my angles, I can use either Pythagorean theorem or trig to help figure out what my sides are. And again, this Vy, what is that? That's just the velocity going up when that object starts. So our Pythagorean theorem and our SOHCAHTOA is going to be really important. So make sure we do know and memorize all of the trig functions so that you can apply that and extract the information you need. Let's keep moving forward. Something important to talk about is the vocabulary word range. The way we've been using it in equations is d sub x, meaning the displacement in the horizontal direction. Another word for that is called range, just meaning how far that projectile went. That's just the displacement in the x direction. Make sure we remember that. That's important because if you see the word range, remember that's just the synonym for displacement in the x direction. Now, there's a couple other things to think about with projectiles, but we know that if you launch something on a high angle or something on a small angle, believe it or not, high or small can end up having the same range. In fact, the rule is when two different angles that you launch at, those two angles add up to 90, you'll actually end up in the same spot. So if you take a look down in the bottom right here, say I launch something at 75-degree angle, it lands here, 10 meters away. But say 75, if you add 15 to that, you get 90. It's the same thing. If you launch something at a small 15-degree angle, it'll land in the same spot as well. So interesting enough, if you have complementary angles where they're added up to 90, even though the height, the dy, the displacement in the y direction will be different, they'll actually land in the same spot, so their dx will be the same. Isn't that kind of interesting? Something to think about. So when we have a projectile, we know it's launched on an angle, we call that theta. The highest point, we can call h as height, or sometimes when we're just looking for the highest point, we call that the highest displacement. And then the r is range, which a lot of times we just call dx, standing for the displacement in the x direction. But again, we're laying down the foundation, we're laying down the vocabulary so that when we hear questions, read them, and think about them, we can start applying it so we can get to the math and solve the problems. The last thing I want to talk about is when we have a projectile, remember, if it's predicted like the 15-degree one at 10 meters, it'll land. It never will really land at 10 meters. It'll always be just a little bit less. Why? Because in real life, there is air resistance. So we've done a lab with our steel marble, and we know that we predicted how far that marble would launch off the ramp. But even though there is very little air resistance, we know that that marble landed slightly shorter distance than it would normally have, according to math. Why? Because of the air resistance. It's just part of reality. We live in an atmosphere. So something to consider, but remember what range is. Range is your displacement in the x direction, horizontal. All right, so here is an example of an angled projectile, right? And this, of course, this angle is our theta. Now that it is launched at an angle, we can break this up into its velocity x component and its velocity y component. Now remember, Vx, velocity in the x direction, stays constant throughout. So whatever, say it started at 20 meters per second, your x direction velocity would be 20 meters per second every single second. It's just constant. But Vy is a different story, right? If you start with an initial velocity upwards, every second it goes higher, it gets 9.8 meters per second slower. And then eventually at the top, the velocity in the y direction is 0. And then every second, it gets 9.8 meters per second faster downward for each second. So this next second would be another 9.8 meters per second. So about negative 19.6 meters per second. So as we go up, we slow down, we stop. and then we speed back up again. Things we've always noticed in everyday life, but now we can put math behind it and an explanation behind it. All right, something cool about angled projectiles is that you can get into satellites. Once you get far enough away from the atmosphere and lower air resistance, you can actually launch something into orbit, and that's what a satellite is. Believe it or not, a satellite, once it's officially pushed and has its horizontal velocity, you push it so hard that as gravity pulls it down, it's going fast enough horizontally that as gravity pulls it, it forever falls around the Earth. Isn't that amazing? So a satellite, literally, once it's initially pushed to a certain speed, it never stops because it's going so fast horizontally that as it falls, it just forever falls around the Earth. I think that's amazing that we figured that out. So those satellites that are helping us with cell phone communication, with GPS, with just mapping the Earth, and Big Brother watching over us, that's all just falling objects, but they fall forever because they're going so fast horizontally. I think that's really cool. So how fast do you really have to go in order to launch something that way so that as it falls, it just falls around with the curvature of the Earth? The incredible thing is that when you go 8,000 meters forward, planet Earth drops about 5 meters. So you literally need to go 8,000 meters that way before it drops 5 meters this way. I mean, guys, that's really fast. So in order to be a satellite, you have to be going horizontally really, really fast. About 8,000 meters forward before gravity makes you fall 5 meters. But pretty crazy to think about, but that's how planet Earth curves. Every 8,000 meters, it drops about 5 meters. All right, cool. So now that we know a little bit more about angled projectiles, let's try two of our first problems from our angled projectile motion worksheet. Here's number one. Let's start kind of drawing out the idea and then using our math chops to help solve for it. Could be Fab 5, could be sine, cosine, tangent, could be Pythagorean theorem, could be the idea that we know that the velocity in the horizontal is always equal to its displacement divided by time because it's constant. Let's dive in. So Esther dives off a 3-meter springboard. Okay, I don't even know if that's really important information or if they're just trying to be tricky. And initially bounces up with a resultant velocity of 8 meters per second at an angle of 80 degrees to the horizontal. Okay, so that means I have an 8 meter per second velocity, and that is 80 degree angle from the horizontal. Okay, so that's what that's telling me. So here's like the ground, the horizontal. All right, I want to know what the horizontal and vertical components of the velocity is. Oh, okay. So if I know the resultant, I can draw in the x, vx, and y components. So really all they're asking for is what is the bottom and the right side of the triangle? Because if we know this is the resultant, then we know the resultant comes from the addition of the x and y components. So we can actually calculate that. All right, let's start with the Vx, though you could start with Vy, it doesn't matter. If I'm trying to find Vx, there has to be a relationship with trig somehow. Now, I already know my hypotenuse, right? 8 meters per second is the resultant. That's my hypotenuse. And I have an angle of 80 degrees. So if this is my theta, if this is the angle, the perspective I'm viewing from, then Vx really here is my adjacent, and 8 meters per second is my hypotenuse. Okay, so what trig function uses adjacent and hypotenuse? That would be the ka and SOHCAHTOA. That would be cosine. Okay, so what I'm going to do is I'm going to take the cosine of that angle, and I'm going to set that equal to my adjacent side, which is Vx. I don't know what that is. That's my adjacent side, divided by the hypotenuse, which is 8. Cool. Now that I have that, I just need to use my algebra. I'm going to multiply both sides by 8, get rid of 8. So my velocity in the x direction is really just equal to 8 times the cosine of 80. So I would literally just type that into my calculator. 8 times the cosine of 80, and I end up getting about 1.39. And since this is velocity, it's meters per second. So look at that. I already figured out my velocity in the x direction, and that's going to stay constant throughout. That is going to be 1.39 meters per second in the x direction. Cool. Now, it wanted me to also get the vertical component. Remember, vertical is y, horizontal is x. So that means I need to solve for my vertical, my Vy. Sorry, that color might not be good to use. Let's use red again. Okay, so I'm gonna look, my Vy is over here. If you look at it from the perspective of theta, this is the opposite side, and I still have my hypotenuse over here. So what uses opposite over hypotenuse, SOHCAHTOA? It would be sine. So I'm actually going to do the sine of my angle, which is 80, is equal to the opposite side, which is actually be solving for my velocity component in the y direction, divided by the hypotenuse, which is 8. So there we go. Now I've got that. All I have to do is my math. I'm going to multiply both sides by 8, get rid of 8. The velocity component here is going to be 8 times the sine of 80. And I'm literally just going to plug that in. 8 times the sine of 80, close parentheses, hit equals, and I get about 7.88 meters per second. All right, so you hopefully wrote that down, followed along, and put that on your worksheet. You have your two answers. The x component is 1.39 meters per second, and the upward y component is 7.88 meters per second velocity. Those are the x and y component. Remember, in a projectile, x and y's act independently of each other. And the way we show that together is through the angled vector, which is called the resultant. All right, hopefully that helped tiptoe into the world of projectiles. Let's try the next one, which steps it up just a little bit, and that way we'll get our feet wet with projectiles. Here we go. All right, so our last question is Ferdinand the Frog is hopping from lily pad to lily pad in search of a good fly for lunch. Okay, so the frog is hopping. A frog is like a projectile because once it launches into the air, only gravity is acting on it, and the rest is just, the horizontal velocities from momentum carrying it forward. So if the lily pads are 2.4 meters apart, all right, so if I have a lily pad and a lily pad, and they are 2.4 meters apart, good to know, and the frog jumps with the speed of 5 meters per second, and he's jumping on an angle, I'm assuming, so let me write that. I'm guessing that's like a resultant, 5 meters per second on an angle, and it takes that frog 0.6 seconds to land on the other lily pad. That's a time. I don't know if I need that, but that's a time. At what angle must Ferdinand make each jump? Oh, okay. So we know the velocity resultant is 5 meters per second. We know that has an x and y coordinate to it, but I really want to know this angle, theta. So that's what I'm trying to solve for. So the frog jumps from one lily pad to the other, and we have a few pieces of information. I know how long it took. I know the resultant velocity that he started with, and I also know the distance that frog jumped, which, by the way, that would be the displacement in the x direction. So it looks like I have time is equal to 0.060 seconds. My displacement or range in the x direction is 2.4 meters. My resultant doesn't really help me because it's not x or y, but I might need that. That's the hypotenuse, so I might need to use trig. Don't forget, anything in the air is gravity, so negative 9.8 acceleration isn't a bad idea, A or G, depending on how I look at that. I've got that too. Now let's see what we can do, how we can figure this out. I want to find the angle, and if I need to know the angle, I'm really going to need to know one of the other sides of this triangle. Because if I know two of the sides, can I use like sine, cosine, tangent to figure that out? And yeah, the answer is yeah, I can. And you know what? I can actually figure out, oh, this could help too. I can figure out my Vx because I have time already and I have horizontal displacement. So I could find out Vx, which is the horizontal velocity, and then from there, since I'll have that in my triangle, I can then use it for the Pythagorean theorem, or no, not the Pythagorean theorem. I could use that for trig. Okay, so this is a good one. I like this. So we've got our givens. Our unknown that we really want to solve for is theta, right? In order to get theta, these are the equations I think I'm going to need to use. If I can use this equation, I can solve for, most importantly, Vx. The reason I want Vx is because velocity in the x direction and my hypotenuse of 5, if I have those two numbers, I can figure out theta. So if I do that, once I figure that out, then from this angle theta, this would be adjacent over hypotenuse. That would be cosine. So if I took the cosine of theta and I did adjacent over hypotenuse, I'll be able to solve this problem. Because remember, my adjacent is going to be Vx. I love this. Okay, so it looks like I've got a two-part problem here. So let's get to work. First thing we're going to do is use our horizontal velocity equation. Vx is going to be equal to the range, which we already know is 2.4 meters. That's how far the frog jumps from leapfrog to leapfrog. And we know the time is 0.6 seconds. So if you do 2.4 divided by 0.6, you end up getting 4 meters per second. Now that we have 4 meters per second, we know that that is the Vx component. So I'm going to erase that, and I'm going to write in my new number of 4. Awesome. So now I have a hypotenuse of 5, and I have an adjacent of 4. So if I do the cosine, which is adjacent over hypotenuse, I'm going to take cosine of theta. I don't know what the angle is, right? So that's like my x. But I know cosine is adjacent, which is 4 meters per second, divided by hypotenuse, which is 5 meters per second. I get 4 divided by 5. If I do 4 divided by 5, I end up getting the decimal 0.8. Now I know that cosine of theta is 0.8. I just need to solve for theta. To do that, remember, to get rid of cosine, I just need to, in my calculator, take the inverse of cosine and put 0.8 in the calculator. If I do inverse of cosine, so second cosine, 0.8, hit the enter button, what am I going to get? I'm going to end up getting about 36.87 degrees. There you go. So that frog jumped at 5 meters per second on an angle of 36.87 degrees. And that's what it wanted. It wanted the angle. Now, if it wanted to get more specific, though, you could have drawn it different ways. For me, since I drew it this way, technically that angle would be north of east. So I could get more specific. However, I'm fully aware that you could have drawn the frog jumping the other way. In that case, it could have been north of west. But anyways, you end up with a degree for the angle using trig. But first, that was tricky. You had to use the equation for your horizontal velocity with what you had because you had the range and the time to figure out the horizontal velocity, and then you could use cosine to figure out the angle. But there you have it. Hopefully you followed along, showed your work, and did for number 2. From there, we can now move forward with the rest of the worksheet. And I think it'd be good for us to work together some more on some of these. So let's go ahead and do that. Take care, physics fam. Love you guys. Best of luck, and keep digging into these equations. There's a lot of power in them. Take care. Be well.